Dear students, today I will give you a brief introduction about UV visible or electronic spectroscopy of molecules. Okay, so here when you are talking about this UV visible range, it's about 100. It's about 100 to 780 nanometer. You can see that means the UV visible range. Actually, this UV visible range can be classified into four. So one is your visible range. Another one is your near UV range, and you can also write this far UV range, and also you have the vacuum UV range. So this is the four regions of UV visible spectroscopy. So in this visible is coming around 400 to 780 nanometer. So in this you can see 400 to 780 nanometer, this visible region is coming. And the next one is near far UV and vacuum UV. Okay, so here near UV is coming around 250 to 400 nanometer, and your far UV is coming around 190 to 250 nanometer, So, and the last one is your vacuum UV region. So this region is not so useful for our molecular characterization, but still it is there. This vacuum UV region, what happens, it's actually you can see below 190 nanometer. So here actually the molecules of air will absorb the mainly oxygen and nitrogen. So there what happens actually, so for to study this vacuum UV region, so you need some special instrumentation chamber. That means you need an evacuated chamber. So it is not so helpful in this vacuum UV region for the molecular characterization. You can take this region, that means visible region, near UV region, far UV region for the characterization of molecules. Actually, what type of molecules you can characterize using this UV visible radiation? Normally, you can characterize the compounds with multiple bonds, and normally aromatic conjugated systems. So mainly it is applicable for this type of molecules. But visible electronics, that means electronic spectroscopy, will give you many ideas about the structure of the molecule. Okay, other type. So mainly it is applicable for multiple bonds and aromatic conjugated systems. Okay, so we will first we will look into the laws of absorption. So that actually the basic thing about this UV visible electronic spectroscopy. Then after that I will tell you specially about this electronic spectroscopy. Okay, so I will I am going to explain you the absorption, the laws of absorption, or the absorption laws. Absorption laws. Okay, now the absorption laws, there are two types of absorption law, already you know. So one is called Beer's law, and other one is called the Beer's law, and other one is the Lambert's law. Lambert's law, Beer's law and Lambert's law. So in order to understand this Beer's law and Lambert's law, just I like to plot a simple instrumentation setup of this UV visible spectroscopy. Okay, so let us start from the source. There is a source of radiation, and there will be a monochromator. So what is the purpose of this monochromator? Monochromator is for the selection of wavelength, and the radiation will pass through a cuvette. So cuvette is known as the sample holder. So it will go to a cuvette, and where your sample is there. So you can see your sample here. Let's take the sample solution here. You can also write sample here, and after that what will happen? So the light will pass through the sample, your sample, and some amount of light will be absorbed by the sample, and the other radiation, the remaining radiation will be transmitted through the sample, and it will come to the detector. It will come to the detector here, and and you can record the spectra. Okay, so this is the simple setup of this UV visible electronic spectroscopy, and you see this cuvette. So actually this Beer's law, you know that there are two factors that is very important here that actually governs this affecting the absorption. So Beer's law is telling the first one, that means your absorbance. So absorption is actually measured in terms of absorbance. I will tell you what is absorbance later. Absorbance is directly proportional to the concentration of solution. So what is the concentration of solution? Means that is a sample concentration, and the other law, Lambert's law telling that this absorbance is directly proportional to path length of the sample. It directly proportional to path length of the sample. So what do you mean by path length of the sample? Okay, so this is a cuvette. You see, this is actually made up of a quartz crystal. So you can see sample is inside, and you can see this particular length. That means this particular length that light is passing through, you can mark it as L. This is known as the path length of the light. So path length is also dependent. So normally for this cuvette, conventionally you can see that it is 1 centimeter. So the Lambert's law is telling that absorbance is also proportional to the path length of the sample. So now we can just express it mathematically. What is called the Beer-Lambert's law. So both the laws, that means Beer and Lambert laws are talking about the absorbance. So both the laws are talking about the absorbance. Then you can write that what is this absorbance. Okay, absorbance. So now you can gradually you can define what is this absorbance. As actually it is a measure of the absorbed light by the sample. So we have to express it. That is the only challenge we have. So we can express it mathematically. So I am telling you the absorbance is the measure of light absorbed by our sample. Okay, so that is your absorbance. Okay, so I will write here these two laws. Absorbance is proportional to concentration of solution, and also absorption is proportional to path length of the sample. Okay, so absorbance, that can be represented by A, is actually proportional to C into L. You can write what is your L. L is known as the path length and C is the concentration of the sample. Okay, so you can also write the absorbance proportionality constant. You can replace by a particular term called epsilon, epsilon into CL, epsilon into CL. So what is this epsilon? So epsilon is known as the molar absorptivity, molar absorptivity coefficient. It is known as the molar absorptivity coefficient. Okay, molar absorptivity coefficient, or sometimes molar absorption. I think it is molar absorption coefficient. Molar it is known as the molar absorption coefficient, or you can also known as the absorptivity. Okay, I think it's the correct term is molar absorption coefficient. Okay, so what is the unit of molar absorption coefficient? It is liter per mole into centimeter. Liter per mole into centimeter. So that is the unit of molar absorption coefficient. So A is equal to absorption epsilon C into L. So that is this law. This is collectively known as Beer-Lambert law. So these are the absorption laws. And also one more important term I will introduce you, that is known as the transmittance. That is known as the transmittance. So what is transmittance actually? Transmittance can be represented by T. I think in absorption spectroscopic technique, this infrared spectroscopy, you can see that the y-axis was this transmittance in percentage. Okay, so transmittance T can be represented as IT by I0. What is actually transmittance? Transmittance is a fraction of light absorbed by the sample. Fraction of light transmitted through the sample. Okay. So what is transmittance? Transmittance is the fraction of light that pass through the sample. Okay, not absorbed. Absorbed is the reverse thing. Transmittance is the fraction of light that pass through the sample. So that is T is equal to IT by I0. So what do you mean by IT and I0? We will see. So IT is known as the intensity. IT is actually intensity of transmitted light. Then what is this I0? I0 is the intensity of incident light. Okay, so what transmittance is? Transmittance is the fraction of light that pass through the sample. It can be represented by T. So now I think you can also express the absorbance in terms of transmittance. That is possible. So the absorption law you can write like this: A is equal to minus log T. It can be also expressed in the terms of transmittance. Okay, A is equal to minus log T. So minus log T means what? Minus log I0 by IT. Minus log I0 by IT. And also you can represent in many ways. You can also write this absorbance is equal to log 1 by T. So initially you have this A is equal to epsilon CL, that is the molar absorption coefficient into concentration into path length. Also you can represent in terms of transmittance, that is A is equal to minus log t, that is equal to minus log into I0 by IT. That is, so you can also represent log A is equal to log 1 by t. So you can also represent like this, that you check the mathematics of this. You can represent in percentage also, that is 2 minus log 2 minus log t percentage, 2 minus log t percentage. Okay, so actually what is this percentage of t? Percentage of t is equal to, simply it is t into 100, t into 100, transmittance into 100. Okay, so in many ways you can express this absorption laws. So one is A is equal to epsilon CL. Okay, so you can write here, you can completely the law, you can write here this A is the absorbance. A is equal to, actually it is equal to epsilon CL, that is also equal to what? That is also equal to minus log t, that is also equal to minus log minus log I0 by IT, I0 by IT, that is also equal to log 1 by t, that is actually also equal to 2 minus log t percentage. So all these ways you can express this absorption laws. So these are all absorption, the equation, mathematical equation for the absorption laws. So you will find many problems related to this to the absorbance to find out the concentration of the sample, to find out the path length of the sample, so that you can understand how the concentration and the path length and the transmittance, all these things affects the absorbance of the system. Okay, absorbance of the sample. Okay, then I will tell you one more one of the applications of this Beer-Lambert's law, absorption laws. Let us take, so suppose you want to find out the concentration of a particular sample. So this actually this was used in the glucose detection and all in blood. The instrument used was colorimeter. Maybe you are maybe I don't know, maybe you heard about colorimeter. The colorimeter is a simple instrument, very simple instrument. There you can see the source of radiation. It's a small box, it's a source of radiation, and it's a very fundamental instrument. You can see source of radiation, and you can see a wavelength selector, and your sample you can keep maybe in a small cuvette type sample holder. You can pour the sample there, and suddenly it will give the reading. Okay, so there here I can tell you one of the applications of this absorption laws. Suppose you have to find out, suppose you want to find out the concentration of a particular sample, so you don't know about the concentration of this particular sample. So what we will do here, you can prepare a range of samples. Okay, so you can prepare a range of samples. How you can prepare a range of samples? Okay, lesser than this concentration and greater than this concentration. So I think actually we don't know the concentration, but simply we know some range. Maybe this is a trial and error method. You have to find out a range also. Okay, so I am taking this 1, 2, 3, 4, 5 samples. So yeah, my unknown I am representing it as maybe x is my unknown. So this is my x, that is the unknown, unknown sample, concentration sample. These are the known concentration. You see, all others are known concentration. The concentration I know. So by using a spectrophotometer, so that is the instrument for measuring the absorbance of the sample. Okay, so I will just give you a small representation, some schematic representation of spectrophotometer now, because we have the practically spectrophotometers are using to find out the absorbance. Okay, so colorimetric measurement is the very fundamental technique, very fundamental technique. So accurate measurement. So colorimeter is normally depend upon the color. So if there is any visual change of color, you can identify. Okay, so sample sometimes you can identify by color also. Suppose there is a high intense color, means the absorbance will be very high. Okay, so but sometimes the color is not visible for us. Okay, color range and the color is not visible for us. So at that time, mainly you have to find out the absorbance by using a spectrophotometer. Okay, spectrophotometer. So spectrophotometer is the modern equipment. The modern equipment is double beam spectrophotometer for the measurement of UV visible spectra. So I will just give you some idea about the double beam instrument. So in that instrument, so you need the source of radiation that will come through a filter, and it will go to the monochromator. It will go to the monochromator first, and from the monochromator it will go to a beam splitter. Almost all the things are similar. Maybe you already we have discussed in the case of infrared spectrophotometer, infrared spectrometer. So there will be a beam splitter, I told you. So beams, then we need a mirror here, maybe a mirror. So the one beam will pass through. One beam will pass through the sample means actually sample plus reference solvent. This is the reference, sample plus reference sample. Okay, then automatically I told you that automatically it will subtract sample plus reference minus reference. You will be getting the sample signals. Okay, it will be recorded somewhere here. Okay, somewhere here. So this is the setup. Actually this is known as a double beam. This is known as a double beam spectrophotometer. It's called as double beam spectrophotometer. So what happens here? You see the application. How can you draw a calibration curve? This is known as a calibration curve for finding out the unknown concentration. So by using spectrophotometer, you can measure the absorbance, right? You can measure the absorbance A. And this axis, that is a y-axis, you can see absorbance, and here you can see the concentration. So unit you can fix, no problem, concentration mole or something. Okay, absorbance versus concentration. Okay, so here what we here to do, we can find out all the absorbance by using a spectrophotometer. You can find out the absorbance of all the samples. Absorbance you can mark here for a particular concentration. So this can be concentration A, concentration B. We don't know this thing. Concentration something D, or concentration A, B, C, D, concentration E, like that you have. So here you can mark the concentration A. We know the concentration. These things we know, A, B, some D here, you know, E here. So concentration is non concentration, A, B, D and E, and this we don't know. Okay, the concentration. And but we can take, all the, for all the solutions we can, all the samples you can take the what, take the for all the solution, you can take what, you can take the absorbance. Okay, absorbance. So you can mark the absorbance here, suppose for A, B here, and your D here, your E here. So there will be, you can see a linear variation because we are preparing the sample like this. Okay, so there will be a linear bias. So you can see that this concentration range, if you are an experimental chemist, you know. Okay, so if you connect all these things, you will be getting a straight line like this, and now how can you find out the unknown concentration? Okay, so maybe sometimes suppose you are getting your unknown wavelength, unknown absorbance here, absorbance here. So this is your unknown absorbance. Okay, so but you don't know the concentration. So what you will do, you can plot. Okay, absorbance you can plot here, and the concentration you can plot. This is called a calibration curve. So this is your concentration, C. This is your concentration C. So this is known as a calibration curve. So like that you can find out the unknown concentration by using a calibration curve. So the instrument, I am again telling you, the instrument used is known as the double beam in spectrophotometer. Okay, so now I am going to draw a typical absorbance plot when you are getting result, actually the output coming from your double beam spectrophotometer. There is a typical UV visible spectroscopy plot of the molecules. Okay, so here you see, I am especially talking about the UV visible electronic spectroscopy of molecules, that you please keep in mind. Okay, so I am going to draw a typical plot, a typical UV visible spectroscopy plot. Okay, so actually you can see the absorbance here, and here you can see the wavelength of absorption. Wavelength, normally it is represented in nanometer. Wavelength in nanometer, you can see here, wavelength in nanometer. Okay, nanometer. So now you see, this is absorbance and this is the wavelength. So typical plot, wavelength I am just plotting some range here, some 2000 to 3000 something. Okay, for example. Okay, I am just plotting like this. You see, you will be getting, sometimes you will be getting like this means. Okay, so this is a typical plot of molecules. Normally it is for the large molecules. You can see this type of UV visible spectra. Okay, so as in the case of the infrared spectroscopy, there will not be some splitted peaks and that type of things are not there. There is only a wavelength range you will be getting, but this portion is important. Okay, this portion is important. So when you plot the maxima, absorption maxima to this particular region, you will be getting the lambda maximum absorption wavelength, that is known as the lambda maximum. So lambda maximum is a very important value. It will be very helpful for the characterization of the molecule. Especially I told you that the molecules which comes in which it is the multiple bonds are there, and also suppose it is an aromatic conjugated system, this will be more helpful. Okay, so that is the lambda maximum you are getting. Okay, absorbance versus wavelength, and lambda maximum value, suppose maybe it is some 270 nanometer like that, or 250 nanometer or something. Okay, just an example. Okay, so this is helpful for the characterization of molecules. So when you are looking into the lambda, so the plot style, the style of plot of different things, I will tell you something about this. I am not explaining this one, because suppose you have an atom, the electronic spectra style will be like this. It will be getting a narrow peak. Suppose you are taking the UV visible electronic spectra of a diatomic molecule. Normally the style will be like this. And suppose you are taking a large molecule, not diatomic, polyatomic, maybe some polyatomic molecule, you will be getting this type of peak. Okay, so this is all about the introduction about the UV visible electronic spectroscopy of molecules. Surely the theoretical part I have not discussed. So in the next portion I will discuss about the Born-Oppenheimer approximation, and the types of electronic transitions, and what are the factors that affecting the electronic transition of the molecule. So now just a brief introduction I did about the absorption laws and all. So in the next part I will explain you what is this, what are the type of transitions, and the important principle behind the transition of the molecule. So that type of things. Okay, thank you.